Okay. Today we will start unit third, number theory. Okay. First, we have already completed unit 1 and 2, set theory. Okay. And unit 3 and unit 4 from number theory. Okay. We will start first unit third. So there are some basic definitions. Absolute value, what is? You know already mod x value. If it is greater than x minus negative, then it is minus x, and if it is 0, then its value is 0. Similarly, it is signum function. The signum function of a non-zero integer x is defined as signum of x equal to mod x upon x. So its value is either plus 1 or minus 1. Of a non-zero integer. Okay. The signum function defined for non-zero integer. Otherwise, here you will see it is undefined. Okay. So it is defined for non-zero integer. So its value is either plus 1 or minus 1 by with the help of this absolute value. Now, well ordering. What is well ordering principle? Well ordering principle is every non-empty set of a non-negative integers contains a smallest element. That is, there is some integer a in S such that a less than equal to b for all b belongs to S. जैसे हमने वहां पढ़ा थे अभी सेट थियरी में फर्स्ट एलिमेंट जैसे it precedes every other element, बिल्कुल इसी तरह का है. A precedes B for all A, B in S. But here usual order is less than equal to, okay, integers. Okay, so every non-empty set S of non-negative integers contains a smallest. कोई भी collection आप non-negative integers से collection लीजिए, you will get a smallest number in that set. This is what called well ordering principle. जैसे 1 2 3 4 5 ये एक सेट मान लीजिए. So 1 is the smallest member among the other, among all. Okay. So divisibility, an integer a is said to be divisible by an integer b. जिससे आपको डिवाइड करना है that should be non-zero. Divisible by b if there exists an integer q such that a equal to b cube. This is what called divisible. A is divisible by b, and it is denoted by b divides n. This is what called b divides n. The first theorem is in this chapter. This is called division algorithm. Okay, we will use some other applications, and we will use for numerical problems this division algorithm. What is division algorithm? So for given integers a and b, suppose you have two integers. You don't know what is a. Is it either an integer? It is either positive or negative. Okay. So if and b should be positive, yeah, b greater than 0, then there exist unique integers q and r such that a equal to b q plus r, where 0 less than equal to r, strictly less than b. आपके पास कोई भी दो नंबर है a and b, then a can be written as bq plus r for some unique integers q and r. Okay. Representation. This representation is unique for two numbers a and b, where b greater than 0. Then this representation is unique. A can be written as bq plus r, where r strictly less than b and greater than equal to 0. So prove, how we will prove this theorem? Okay. So let us consider the set S is a minus x b, x from z, and a minus xb greater than equal to 0. Okay, this positive integer. Now we will claim that S is non-empty, and for this we will show that a minus xb greater than equal to 0 for some choice of x, and this is since b greater than equal to 1, we have mod a b greater than equal to mod a. Now for choosing x equal to minus mod a, okay, absolute value of a, we get a minus xb equal to a minus of minus mod a b. This is equal to ultimately a plus mod a b, and this quantity you see here mod a b greater than equal to mod a. Okay, since b greater than equal to 1 है, तो ये दोनों साइड सेम है, तो अब कोई भी नंबर बड़ा है इसमें b ग्रेटर, तो इस सेट बड़ा हो जाएगा. It will bigger than this. So therefore this is, and this is greater than equal to a plus mod a. By using this, a mod be greater than, and this is equal to either 0. If a negative, then it is 0. If a positive, then it is twice a. Okay, a plus mod a is a twice a. So this is greater than equal to 0. Ultimately, this is greater than equal to 0. So this means S is non-empty. Our claim was that set a minus xb set should be non-empty. So this is, then by well ordering, so S is our non-empty. So then by well ordering principle, S contains a smallest element because S is the collection of all non-negative integers. Okay. So here we will apply well ordering principle. Okay. So S contains the smallest element and say it is R. Then by the definition of S, there exists an integer Q satisfying R equal to A minus QB. Okay. So A minus XB, we choose X as X is our Q. So our element is, integer is A minus QB. Okay. And we say it is R, we put it as R, smallest one, and this is equal to A minus QB. Because A minus XB is a member of S. Okay. And for this R, we say we fix R because S contains the smallest element and we say it is our R. So that means R is a member of S. So what R will be, कैसे R कैसे फॉर्म होगा, S का मेंबर कैसे फॉर्म है, A minus XB टाइप. ओके, R के मेंबर जो है वो A minus XB टाइप. Okay, so R equal to A minus XB. X, for this R, X is, we suppose X as Q. Okay, so this implies A equal to QB plus R, where R greater than equal to 0. Okay, so 0 less than equal to R. Okay. Non-negative, so it may be 0. Okay, or positive. Okay, so that therefore R greater than equal to 0. Smallest element in R is the smallest element. It may be 0 or may be greater than 0. So therefore R equal to A minus QB, where R greater than equal to 0. And this can be written as A equal to QB plus R, where 0 less than equal to R. अब हमारे एक और condition, we required one more condition. R should be strictly less than B. We need to prove this part. Claim R strictly less than B. Okay, then we will say that our theorem is proved. Okay. Also, we have to prove uniqueness of R and Q. So contradictory, let R greater than equal to, we need to prove that R strictly less than B. Okay. On the contrary, we suppose R greater than equal to B. इसके opposite ले लीजिए. Suppose R greater than equal to B. So that means R can be written as R1 plus B, where R1 should be, where R1 greater than equal to 0. R1 positive, no, sorry, non-negative, R1 non-negative. Okay, you see R equal to B, since R greater than equal to B, तो अब equal कैसे करेंगे? You put some R1 where R1 greater than equal to 0, because R1 is, you see from here, R1 equal to R minus B, and R is your, from given last relation, R is your A minus B QB, या BQ, and minus B. So A minus B common here, Q plus 1. So it is some X. Integer है, integer plus 1 is again an integer. So it is an integer. So A minus integer into B. So this element is a member of, this is a member of S. This is a member of S and greater than equal to 0. Greater than equal to 0. R1 is a member of S and this is greater than equal to 0. So therefore R1 equal to R minus B greater than equal to 0. Therefore this implies R1 strictly less than R. This implies R1 strictly less than R. Okay, because B greater than 0, our B greater than 0, B not 0. So equality, there will no chance of equality. Okay, strictly less than, therefore R1 strictly less than B. Since R1 equal to R minus B, some quantity minus करने के बाद equal है, इसका मतलब this is greater than this R1. So therefore R1 strictly less than R, because B strictly greater than 0. Okay. So which is a contradiction? You see, R1 is a member of S and R1 less than S. How it is possible? You choose R as the smallest member of S. By your supposition, you see, S contains the smallest element and say it is R. R is the smallest element of S. But here you are getting another element, R1. We say here R1 is an element of S. Okay. So we are finding here R1 as a member of S, and which is less than R. But R is the smallest member. How it is possible? So this is a contradiction. So therefore, this implies our supposition is wrong. R greater than equal to B. That supposition was wrong. That means R strictly less than B. So we have our complete proof. A equal to BQ plus R, where 0 less than equal to R and R strictly less than B. Complete means now we will have to prove uniqueness of Q and R. And in this representation, Q and R are unique. ये नहीं हो सकता है कोई सम और Q1 मिल जाए और सम R1 मिल जाए जिससे ये सेटिस्फाई हो. ओके, ये यूनिक Q है और यूनिक R है फॉर दिस A एंड B. इस पेयर के लिए ये जो आपको दो एलिमेंट है आपके पास A and B. Okay, and for this pair, this Q and R is also fixed, unique. Okay, so we need to prove that uniqueness. How we will continue? Suppose A has two representation BQ plus R. ये तो given एक representation हो गए, ठीक है? Suppose we another representation BQ1 plus R, R1. Okay, means Q1 R, ये भी ले सकते हैं आप Q1 R1, Q2 R2. ये एक तो ओरिजिनल है BQ plus R, दूसरा आपने चूज कर लिया Q1 plus R1, BQ1 plus R1. Okay, now our task is to show that Q equal to Q1 and R equal to R1. For this uniqueness purpose, we need to show these things. Okay, so now calculate this, subtract from this to this, because it is also A and it is also A. So A minus A, left hand side 0 and right hand side B, Q minus Q1 plus R minus R1. So this implies R1 minus R equal to B into this. Now take absolute value of both sides. So this is R1 minus R. And if you take absolute value this, then mod B equal to B, since B greater than 0, given. Okay, so B out of mod. Okay, this is Q1 minus Q minus Q1. Say this is relation is star. Okay, this equation is star. Up now you can some other calculation. Since 0 less than equal to R strictly less than B, yeah, it is already proved. This part already proved. Okay, so this implies, and this inequality gives minus B less than strictly less than equal to R minus R less than equal to 0. Okay, ये negative है. This is greater than less than equal to 0. यहाँ से this, and also we have this one. So since for this representation, this is also 0 less than equal to R1 strictly less than B. Like here, since this is we are considering this is another representation, so condition will hold. 0 less than equal to R1 strictly less than B. Okay, this one is here. For this representation we have this line 0 less than equal to R1 strictly less than B. And from here, from first representation, we have find this by changing negative signs, by putting negative sign and change the inequality. So now from these two, combining these two, मतलब these two inequality को दोनों को add कर दीजिए आप, adding भी कह सकते हैं या combining these two. Now combining these two inequalities, we obtain minus R strictly less than R1 minus R strictly less than B. And this is nothing but mod R1 minus R strictly less than B. And using this in star, mod R1 minus R strictly less than B, वहां से हमें from star we will get B into, because इस पार्ट के वैल्यू है हमारे पास B into mod Q minus Q1. You can see from star here. We have calculate this, but this equal to this. So here B into mod Q1 minus than B, and which this yields that 0 less than equal to mod q minus q1 less than 1. You see here, this is strictly less than v by v1. So, and also this is 0 less than equal to, this is absolute value. So it is greater than equal to 0, this part. Okay, non-negative, absolute value is always non-negative. That means greater than equal to 0. So 0 less than equal to mod q minus q1 less than 1. So this is an integer and less than 1. So this integer must be 0. So therefore, you see mod q minus q1 equal to 0 implies q minus q1 equal to absolute 0 means that element is 0. You know, absolute mod x equal to 0 implies x equal to 0. So this implies q minus q1 equal to 0. This implies q equal to q1. Okay. And then from star, we get mod r minus r. If this 0 q minus q1, you see from star, mod q minus q1 0 means b into 0 0. So mod r minus r1 is also 0, and this implies r equal to r1. So you get you take two representations, a equal to bq plus r, and another a equal to bq1 plus r1. Finally, you get q equal to q1 and r equal to r1. Means if two representations are same, that is our representation is unique. Okay. And in this theorem, this unique, we get two numbers, integers q and r. These are called respectively. Q is called quotient and r is called remainder in the division of a by b. In this division, okay, we get two unique integers q and r, and this q is called quotient and r is called remainder. So okay, today this is what we will up to here. Okay, from next class we will start other theorems and okay.
सर इसकी पीडीएफ सेंड नहीं किया आपने?
हाँ बताइए.